Maynard speaking on large gaps between primes and subsets.
Okay, thanks a lot. I'd like to thank the organisers for inviting me to speak, and since this is a current developments in analytic number theory, I thought I would cover the current thing by talking about something that happened whilst we were here in MSRI, and I'll cover the analytic number theorem by having lots of logs in my talk. But before I start, I guess this is going to be joint work. So everything I say today is going to be joint work with Kevin Ford, Sergei Konyagin, Carl Pomerance, and Tao. And the basic question I'd like to think about today is, if you take your favorite subset of the integers, what's the distribution of primes in that set, and in particular, how large can the gaps between the primes be? So, given some set A in the positive integers, how large can gaps between primes in A, B? And what sort of techniques do we possibly have for answering any question like this? So just as some examples, you could take your set A to be the set of all positive integers, in which case I'm just thinking about how large can gaps between primes be. One example that I'm going to touch on several times in this talk is going to be if you took A to be the set of values of the polynomial n squared plus 1. So a much thinner set. More generally, I guess you could think of A being any polynomial, the set of values of any polynomial. And I guess f better be an irreducible polynomial for there to even be a chance of it taking on infinitely many values, and similarly it shouldn't always take values which are multiple of 2, but provided it satisfies a few obvious conditions, even though we don't know such sets in either of these two cases would represent infinitely many primes, we can still guess at how often it should represent infinitely many primes, and maybe you could change the question around to think about how long a string of consecutive composite values could you find in your set. And then another example of set A, which I won't be able to say anything about in the talk today, would be the set of values of p plus 2, where p is a prime. So in particular, for the set of values of n squared plus 1, this was a question of Carl Pomerance. How large can gaps between primes of the form n squared plus 1 be, or how long a string of consecutive composite values of the polynomial x squared plus 1 can you have? And similarly, in this case, for large gaps between twin primes, this was a question of Heath-Brown. Can you guarantee that you get reasonably long strings compared to the trivial bound of twin primes, and you might hope to be able to get lots of strings of consecutive composite values even if you can prove that there are infinitely many primes. So anyway, this is the question that I'd like to think about today, and I mentioned in various cases there's certain trivial bounds. So in particular, we know that the set of primes gets sparser, so certainly the gaps between primes are going to grow in any sequence of the integers, and so we want to think about how large gaps are relative to the size of the integers. So to make my question slightly more precise, I want to think of the set of primes in A being equal to the set P1, P2, and so on, where I'm ordering these primes just by their size. And then the question that I'm really asking is, how large is, let's say, g of x, which is the supremum over primes pj less than or equal to x of pj plus 1 maybe let's say pj plus 1 less than or equal to x minus pj. And can I get a lower bound which is non-trivial in some sense? So although we don't know that there's infinitely many primes of the form n squared plus 1, and we don't know that there's infinitely many twin primes, and we don't know that there's infinitely many prime values of any given polynomial which satisfies the obvious local conditions, you can nonetheless get a upper bound of the correct order of magnitude by just applying a simple low-dimensional sieve. So sieve methods show, let's say that the number of primes of the form f of n, which are less than or equal to x, is bounded above by some constant dependent on a polynomial times x to the 1 minus x to the power 1 over d, which is the number of integer values of your polynomial which are less than or equal to x, divided by 1 logarithm of x. And so in particular, you're saying that the density of the primes in the values of your polynomials at most are constant over log x, and trivially from this, you get that there are strings of log x greater than log x consecutive composite values of f. So there's some n0 such that f of n0 plus 1, f of n0 plus 2, up to f of n0 plus some quantity that's of size roughly log x, are all composite values which are all less than or equal to capital X. And the main question I'm interested in is, in what situations can we do better than this trivial bound, where we can have rather more than just log x consecutive composite values? So based on probabilistic reasoning, you might guess that, in fact, there should be about log x squared consecutive composite values for the sorts of examples of sets that I'm looking at here, which correspondingly gives you large gaps between primes that occur early. And just in the simplest case of A being the positive integers, this is some form of Cramer's conjecture if you make this precise, and this is way beyond anything that we can possibly hope to prove, even if you're assuming Riemann hypothesis and nice distribution of zeros and everything like that. And so we're certainly not going to have realistically be thinking of doing much better than log x, but we want to get something that tends to infinity faster than just log x. And so that's the aim of the talk, and in what sort of sets can I say something like this? So, and I guess prior to our work, the only examples that I'm aware of, at least, where you could prove that there are strings of rather more than log x consecutive composite values is when your set was just the positive integers or something that looked very similar to the positive integers. So maybe some arithmetic progression. So the fact that there are gap stream primes that can be arbitrarily large compared to the average gap is a result of Cynthius from maybe the late 1920s or early 1930s. But this and its subsequent improvements by Erdős and Rankine all relied on a certain trick to do with smooth numbers that was somehow fundamental to method, and that's the only method I'm aware of any case where you can prove more than about log x consecutive composite values. And somewhat disappointingly, this trick doesn't generalize to any of these more general situations, and so it seems quite specific to just the set of integers. So I'll explain this a bit later, but the main result that I'd like to present today is a more flexible version of this argument that shows that for at least the example when we're looking at integer values of the polynomial, you can do better than just this trivial bound of log x, and you can get rather longer strings of occasionally getting consecutive composite values of your polynomial. Yeah, sure. Mm-hmm. Sorry, you're saying you.
If you look at the value, you've got your polynomial f,
Mm-hmm.
and you look at the value, you evaluate it at a particular integer f of n, plus n, where n is a number integer between 2 and n. Then for polynomial identity reasons, this is always divisible by f of n. It's always constant.
I'm not sure I'm following. So in the case of n squared plus 1, I pick some value n. I then get my value of f of n, which is n squared plus 1. And you're saying that if I take f of n squared plus 1 plus m, which is n squared plus 1 plus m all squared plus 1, yeah, I'm looking. You happy? Okay. I'm not sure I answered your question, but I'll continue. So the result that I'd like to talk about is when we're looking at integer values, we can do better than this trivial bound. So I guess this theorem is due to Kevin, Sergei, myself, Carl, and Terry, and we're saying that given some integer polynomial, and you might as well assume that it satisfies all the obvious local conditions, but I won't bother writing it down, but the theorem's trivial. If this isn't the case, there exists at least some constant depending on f of log x times log x to some small positive power. So I'll call this epsilon f, because the exponent here will depend on the polynomial. Consecutive integers such that f of n is composite. And less than equal to x. So we're doing better than the trivial bound of log x by some factor log x to some small power. I guess the other thing I should probably mention is that since this is a current topics talk, this is still a relatively new result, and so we still finalizing all the details of the paper. So there's the usual proviso for any work in progress talk that there's a small risk that some of the constants and quantities might change when the paper actually finally comes out. But anyway, this is the result that we're pretty sure that we've proven. So is everyone happy with the statement of the main theorem? Okay, so how do you prove any of these results about large gap stream primes? Unfortunately, there's only one approach that we as a community have at all for proving anything non-trivial, and this is some silly argument based on the Chinese remainder theorem that turns the problem into a sieve game. So this is the following lemma that's behind every proof of every result about large gap stream primes, essentially, apart from maybe one or two small results of Erdos. So there's a game where you have to try and choose residue classes modulo lots of small primes to efficiently cover some interval 1 up to y. So if there exists a choice of residue classes AP modulo P for all primes P less than or equal to X, such that if you take any integer n between 1 and y, there exists some prime P less than or equal to X, such that f of AP plus n is congruent to 0 modulo P. Then there exists y consecutive composite values of f of n, all let's say with n less than or equal to some constant dependent on f times the product of all primes less than or equal to x. And I'm not going to prove this here, but the proof is just the Chinese remainder theorem. So maybe I lied when I said I wouldn't prove it. So this maybe looks like a slightly messy formulation. It depends on two quantities, x and y. But what I like to visualize in my head is you write down all the integers between 1 and y, and then you're going to go through the primes in consecutive order, and you're going to cross out a whole load of integers according to their residue classes. And the game is how I want to choose these efficiently so I can cross out all the integers 1 up to y as quickly as possible. So in the case we're thinking of the polynomial f of n equals n, this is the standard case of large gaps between prime numbers when we're looking at just integers, and you cross out everything which is congruent to a2 modulo 2, then a3 modulo 3, then a4 modulo a5 modulo 5, and you keep on going until you've crossed out all integers between 1 and y. And the question is, how do you choose your residue classes AP cleverly to cross out all the integers between 1 and y as quickly as possible? If you instead had the polynomial f of n is n squared plus 1, it's a similar situation, but it's slightly different. So you first cross out everything in the residue class a2 modulo 2. You then don't cross out anything in the residue class in residue classes modulo 3, because n squared plus 1 is never a multiple of 3. But then modulo 5, you cross out a5 plus or minus 2 mod 5, and in general, you're crossing out AP plus or minus the square root of minus 1 modulo P for all primes which are 1 mod 4. And the game is exactly the same. You can choose your APs completely freely, and you're crossing these out, and you want to cross out all the integers between 1 and y as quickly as possible. And the game is, how quickly can you cross out all the integers between 1 up to y? So I've already said there's one trivial way of getting log x consecutive composite values. here's another trivial way of getting log x consecutive composite values based on using this lemma. And that's just to choose all your residue classes greedily. So the second trivial attempt is choose AP mod P greedily to remove as many as possible at each stage. And so you can split your primes into two classes. You can think about small primes, which are, say, primes less than or equal to x over 10, and then large primes, which are maybe primes between x over 10 and x. And for the small primes, if we're choosing them greedily, we're certainly removing at least the average number of things that you'd remove. And so we're removing a proportion NP over P, where NP is the number of roots of f modulo P. So in the case of just f of n equals n, we're at every stage for these small primes, we're certainly removing a proportion 1 over P of the possible residue classes. But this is quite inefficient when the primes start getting pretty large. And so for the large primes, if we're choosing it greedily, we're just going to note that you're removing at least one element each time. So after I do this for all small primes, I'd be left with a set of size, well, I started off with a set of size y, and I'm losing a proportion np over p each time. So a set of size at most 1 minus the product of np over p over all primes p, which are less than or equal to x over 10. And this quantity here is approximately some constant times y over log x. Because on average, the NP is going to be 1 whenever f's irreducible. So in particular, this means I would remove everything if the number of large primes I have is bigger than the number of survivors from the small primes. And so this means we can remove everything if y is some constant dependent on f times little x. Just because the number of survivors here is smaller than the number of big primes, which is then removing at least one each time. And so when you translate this numerology back through this lemma, this gives you precisely this statement proven in a different way, that there's strings of about log x consecutive composite values of any polynomial. And so we now have two different trivial arguments that both prove the same result, which is just too weak by a little bit from what we want to prove. Yeah?
So what did you say the conjecture was again, and what's the limitation of the Chinese remainder methods?
So that's a very good question. So based on probabilistic reasoning, for most sequences that have similar properties, you might guess that there should be about log x squared, or log x to the 2 plus little o1 consecutive composite values of any polynomial. However, whenever you go through this Chinese remainder theorem method, you're not really just finding any old typical composite number. You're finding composite values where you're looking at numbers of size, maybe x, that have a prime factor of size at most log x. And so these are quite atypical composite values. And again, we don't know for sure, but it's conjectured that this actually places pretty severe restriction, and you can't do better than log x to the power 1 plus little o1, and in fact, probably of size log x times log x to some exponent by going through this Chinese remainder theorem argument. So in particular, we're getting log x times log x to some exponent, maybe our exponent isn't optimal, but but this whole Chinese remainder theorem argument really puts a very strong restriction on things. I guess you might speculate that actually the sorts of quantities that we're getting out in our theorem are pretty close to as good as you could hope to do if you're going through this sort of Chinese remainder theorem argument. So this is the only way we know of how to do anything, but this places a very strong restriction on what you can possibly hope to prove. Okay. Are there any further questions? Okay. Seeing no further questions, I want to recall how Cynthius and then Erdős and Rankin were able to do better than the trivial bound by a modification of this argument using this trick to do with smooth numbers, and then why it doesn't help for consecutive values of a more general polynomial. So rather than just choosing these APs greedily, the Erdős Rankin trick is to note that it's unusually efficient to choose AP to be equal to 0 for the vast majority of medium-sized primes. So let's say for primes between some quantity z, which we can think of as being small, but I'm not going to specify at the moment, up to x over 10. So what's the point of doing this? Well, imagine we're in the integer setting, we're removing all the things that are multiple of any prime between z and x over 10. So if we did this first, we'd be left with things that are z smooth, or have their one prime factor of size maybe between x over 10 and y, and some remainder factor which is z smooth. And it turns out that this is unusually efficient because both of these different factorization types are very unusual factorization types for integers. That typically, when z is smooth, you should think of most integers having a z-smooth part of size z to some positive constant, whereas here we're having a z-smooth part which is of size basically y. So if z is small compared to y, this is a much, much larger z-smooth part than a typical integer. And similarly here, we have some prime times some small z-smooth part, which is of size about y over x. And if y over x is a lot smaller than z, then this is, again, an atypical factorization. And because we can explicitly say what these factorizations are, and both of these factorizations are atypical, this means that this sieving step actually produces rather fewer elements that survive it when we're crossing them out than just some typical greedy random choice. And so, in particular, if you do this, then at least for for z appropriately small compared to y, and y over x appropriately small compared to z, you get that there should be log y over x times y over log x survivors instead of the product, y times the product of 1 minus 1 over p for p between these ranges, which would be log z times y over log x. And so because you are more successful in this step, you can then be completely greedy for all the small primes less than or equal to z, you get a factor 1 minus 1 over p. You can then do this, removing one large element for the primes bigger than 10, and because you are more efficient here, you have fewer things by an arbitrarily large factor, and so you can improve on this bound by an arbitrarily large quantity. And then to get the optimal quantitative result, it's just a matter of optimizing all these quantities in terms of z using smooth number estimates. And that's the whole Erdos-Rankin argument for getting large gap stream prime numbers. And again, this is basically the only way we know of how to prove large gap stream primes using this trick about smooth numbers. But if we tried to do exactly the same thing for, say, the polynomial f of n equals n squared plus 1, well, we can still choose AP to be 0 for all these medium primes. There's this slightly annoying thing that we're only dealing with primes which are 1 mod 4, but that doesn't really matter too much. We'll get that we're only left with n up to y such that f of n has no medium-sized prime factors. Prime factors. So in particular, any prime factor has to be bigger than x over 10. So either f of n looks like some z-smooth number, which is a very rare occurrence, or it looks like some z-smooth number times 2 large primes, which means the z-smooth part has to be very small again, and this is again a very rare occurrence. Or f of n looks like some prime times some z-smooth part. But this prime times the z-smooth part is not a rare occurrence at all, and it's this slightly technical point which causes the whole trick to break down. Because you no longer have any control over the size of the prime or the size of the z-smooth part. And it turns out that when you do this quantitatively, it gets you precisely what you'd have got if you just chose everything greedily. And so if you want to make any progress, you're going to have to abandon this choose an AP equals 0 trick and do something that doesn't involve smooth numbers. And so this is what I'd like to briefly talk about today. And our work is still based on using this Chinese remainder theorem argument and is still using quite a lot of greedy or random arguments for most of the fairly small primes, but when you get to largish primes, we want to be more efficient. And so in particular, there were 5 of us who worked on improving the Erdos-Rankin bounds for large gap stream primes. It was a well-known problem of Erdos as to whether one could improve on the quantitative sizes of the gap stream primes. And we were able to do that by a similar argument, improving the efficiency of largest primes, but all of that argument relied on somewhat delicate estimates to do with linear equations in the primes, to find unusual residue classes that were unnaturally efficient. So in our case here, we're going to use very little arithmetic information about the primes. So in some sense, we're not really using much more than the prime number theorem. However, the slight difference is because we weren't helped by this Erdos-Rankin trick, we need to fight a bit harder to win enough to make sure that we can actually get a non-trivial bound. Whereas in the case of improving the previous Erdos-Rankin arguments, it was clear that as soon as you had certain strong enough results about primes and arithmetic progressions, you just needed a little bit more to win over their argument. So instead, we can try choosing AP, well, I guess maybe for the sake of clarity of argument, I'm going to just consider the case f of n equals n. So everything I say will generalize totally naturally to more general polynomials, but notationally it saves a few side cases. And so I'm just going to talk about proving large gaps between primes in a way that will generalize to polynomials and doesn't use this trick about smooth numbers at all. So and now I'm going to choose AP to be 0 if primes are very small, let's say less than z to the 10, whereas these are free parameter that I'll choose later. For most primes, so let's say for primes between z to the 10 and x over z, I want to just choose them as IID uniform random variables. Then for largish primes, so primes between x over 10 and x over z, I want to choose them randomly, but conditional on the previous random choices. And then for the very large primes between x and x over 10, I'll choose them greedily as before. So I am choosing these APs to be 0 for the very small primes. This is just a very minor technical thing. I'm not using smooth number estimates at all. This isn't really necessary, but it's just to try and ease the explanations as to what the key ideas are. So I want to think about doing them in these stages. So first of all, I sit by the smooth primes. This is totally deterministic. I just get left with all the integers between 1 and y that have no prime factors less than or equal to z to the 10. I then do this random sieving where I'm just choosing my APs uniformly at random independently for all of these different primes, and this is the vast majority of the primes. So once I've done that random sieving, I'm left with some random set of integers. And so if I call this stage 1, this stage 2, this stage 3, this stage 4, after 1 and 2, I'm left with a random set of integers and the size of this set, well, you might guess that it should, each prime should behave independently. Each one would reduce on average maybe a proportion 1 over p. So this is for primes p less than x over z. And it should have this size with high probability. So morally, we think of this set as having a fixed size, even though it's a random set. And I want to think about what I can do for one of these largish primes and how I can choose it to pick a residue class that's going to perform particularly well. So let's think about and I'll call these large primes Q just to distinguish them from generic primes. So Q will be a prime in the range x over z to x over 10. And think about just one residue class n mod Q. So initially, this has about y over q elements. But I then perform the sieving by the small primes, and I am inevitably going to knock out some of the elements of this residue class. So after stage 1, I get some deterministic set. And this will have about y over q log y over q elements. And I'm then applying my stage 2, which is my random choice. And so after stage 2, you would typically have, well, you'd have about y over q log y over q, the number of things we had before, and then you'd typically remove a proportion 1 over p for the p of stage 2. But at least when z is pretty small, it turns out that this is actually, and y is pretty close to x, this is actually less than 1. And so typically you're not having any elements surviving in any of the residue classes. And so if you were just choosing randomly, independently of everything that happened before, this wouldn't be a very good way of doing things, because you'd be typically removing nothing for any of these moderate primes. And so in particular, when we did our greedy argument before, we would just be removing one element here. It wouldn't be very efficient. However, occasionally, you expect many more. Roughly because I should think about removing any one of these elements with probability about 1 over q, 1 over p for each of the medium primes p. So in fact, you might guess that all of the y over q log y over q things that I had before should actually survive with some positive probability. Oops. So what's the probability that any one of them would survive? Well, that'd be probability about 1 minus 1 over p for all p of stage 2. And the probability that all of them survive, well, maybe these are all independent, so this would be that quantity to the power y over q log y over q. So this is going to be a pretty small quantity. However, the product over all primes for stage 2 you can think of as maybe 1 over log x. We can think of y as being pretty close to x. And so this is maybe of size about log x to the minus y over q, if we're being very rough. And if z is pretty small, this is going to be a reasonably small thing, but it's going to be not so tiny compared to the almost x number of choices of the residue class. And so in fact, we expect there to be many different unusual residue classes that survive all the medium prime sieving. And so then one idea to get large gaps between primes would be to just choose the residue classes for these primes uniformly at random amongst those residue classes which are unusually efficient and have had this occasional effect of not being sieved out at all. And this way, we expect for each of these large primes, P in this region, that rather than just removing one element, we're instead removing all of these y over q log y over q elements. And so we're being much more efficient for these primes in stage 3. And if somehow all of this sieving was done totally independently of one another, you'd expect, rather than us just removing one, we'd be removing about this many each time, and we'd be much more efficient, and hopefully would improve large gaps between primes.
What's the motivation behind the idea for stage 2, and it's sort of like removing complex classes randomly is the best way to use this Chinese regime?
Yeah, so somehow when you have, so stage 2 is not doing anything intelligent whatsoever. It's just getting average case behavior. But somehow whenever you have a small prime, you're always going to be removing a proportion 1 over p of whatever natural looking set you have, unless there's some very bizarre conspiracy going on. And so in particular, unless you're very able to prove something very clever and structural, like maybe the Erdős ranking trick, you can't really expect to be doing much better than this, because you're not going to be, concentration of measure will suggest that you're not going to have many fluctuations in amongst the different residue classes of the number of things you want to move. So I guess intuitively you might think that for primes which are moderately small, you shouldn't really be expecting to be able to do much better than just the trivial greedy choice. But the advantage of choosing everything completely at random is that you can get a huge amount of extra entropy into the system, and so you can then start making all these conditional choices, and you just need to show that average case behavior is nice. And so sort of some sort of concentration of measure type effect might say that virtually all the time you have a set of this size, and therefore you don't need to worry too much about the particular structure of the set. Whereas as soon as you made some concrete deterministic choice of these small primes, you'd suddenly need to understand the precise structure of that set in a huge amount of detail, whereas choosing it randomly means that you don't need to worry too much about the precise structure of the set at all. Yeah, so we're not winning anything at all from choosing things randomly, other than in the proof, it means that we just need to consider average case behavior at every stage, and this makes proving actual statements about the harder cases when we're choosing things conditionally much, much easier. Okay, so this is our idea. Independently for each prime p between x over 10 and x over z, choose uniformly amongst these good residue classes. And again, we're still choosing this randomly, and we're choosing it independently for all primes, so we want to think that the randomness is going to help show that typically there's independence, and therefore at least there must be some choice where we have all properties as if they were completely independent from one another. So let's think about what happens in this situation. So let's at least try and guess the probability that some integer n survives stage 3. Well, since all of the sieving is done independently for each of these primes, all the choices are completely independent, the probability that it survives is the probability that it survives the sieving for each q in this range, which is just 1 minus the probability that n is sieved out by q. And since we're thinking of these probabilities as being small, we can just bound 1 minus x by e to the minus x. And so then this will be x of minus the sum over all q between x over 10 and x over z of the probability that n is sieved out by q. And this is just the expected number of times that any integer n would be sieved out. So if the expected number of times that n is sieved out is, say, at least t for all n surviving stages 1 and 2, then the expected number that would survive stage 3 would be a proportion at most e to the minus t. So the number of things that survive 1 and 2 is about y over log x. And then the proportion that survive stage 3 would be an extra factor e to the minus t. So this is on the assumption that for all of these n's, the expected number of times it sieves out is bigger than some quantity t. And this means that we'd have at most this number of survivors for some deterministic choice. Since the expected number is this big, there must be some deterministic choice of the APs, which gives something of that size. But then if this is less than the number of very large primes in stage 4, then we can remove everything just by removing one thing for each of those very large primes. So that means if y e to the minus t over log x is less than, say, x over 2 log x, then we can cover all of the integers 1 up to y. Yeah.
So where's this y over log x? Wasn't your worst case for stage 2 on the bottom in that lower board there?
Yeah, so it's just this quantity. So this is of size about y over log x.
Well, sure, but then you had a worst case on the other board right at the bottom.
Yeah, so
Accounting for the worst case.
no, so there's two separate things going on here. So I take my full set 1 up to y, I then sieve deterministically in stage 1, and I sieve randomly in stage 2, and almost surely I'm left with something of size y over x as the survivors. Then this aside was thinking about one individual residue class. And it was saying that typically you'd have the number of things in the residue class divided by log of x, which is less than 1, and that's useless. However, occasionally you can do rather better than this. And in particular, because you can do rather better than this, if you always had this expected number of things being sieved out, then you'd remove an extra proportion e to the minus t from that initial set I had of size y over log x. So this was talking about one individual residue class, whereas this is talking about the whole set, and this is talking about the whole set. Does that make sense? Okay. Okay, so we have the expected number of integers n, which survives 1, 2, and 3, is of size y e to the minus t over log x. And so this is good for y being of size about x times e to the t. And so in particular, we get an arbitrarily large improvement, provided we can take this quantity t to be arbitrarily large. And so we've reduced all these ideas down to just showing that if you choose your residue classes probabilistically in this way, conditionally on the previous steps, then you want the expected number of times anything that's going to be sieved out is going to go to infinity. And provided you can do that, you can get an arbitrarily large improvement on the previous arguments, and in particular, you can get a non-trivial bound for gap between primes that doesn't use smooth numbers in any way. And so this is now just some probability calculation, and the idea is that because we've chosen everything randomly, the average case behavior should happen virtually all the time, and so there should be a large concentration of measure, and so you can just do several second moment estimates to show that the sieving is essentially completely independent of one another, and so everything's about as uniform as you can possibly expect. But we should maybe check what we should actually expect, because it's not obvious that the expected number of times it sieves out, even if everything is totally uniform, would really go to infinity. So I'm not going to talk too much about the precise probabilistic calculations, but I'll just say choosing everything uniform random implies even sieving, and morally you only need to think about the average case behavior. So in the average case, for every one of these large primes q, I'm removing about y over q log y over q elements. And so if this was completely uniform amongst all my y over log x survivors, I would expect the the number of times any individual n is removed by any individual q to be roughly the ratio of these two quantities in some average sense. So therefore, we would guess that the expected number of times should be approximately the sum over all primes q between x over 10 and x over z of the number of things I remove at each stage. So this should be y over q log y over q divided by the number of survivors I had, which was y over log x. And you can simplify this a bit and put everything into dyadic intervals. So this is then the sum of q equals 2 to the j between x over 10 and x over z of 1 over log y over q. And provided y over x is then little o of z, I think if I've done my calculations right, then this should be of size about log z if y over x small. So fortunately, this quantity does diverge, although it diverges very slowly. And because we're getting, in the average case, a arbitrarily large number of times any individual n is being removed, we can correspondingly take y to be of size a bit larger than x, going to infinity, and then get arbitrarily large gaps between prime numbers and arbitrarily large improvement over the trivial bound of log x. And this is assuming that everything happens in the as if it was just average case behavior. But by choosing everything uniform random, you can show that the average case behavior is the typical behavior. And so outside of some small exceptional set of n's and some small exceptional set of q's, all of these calculations work exactly as I've described. So I'm basically out of time. I hope I've given a motivation for the key ideas in the proof. However, if you really care about the quantitative side of things, and in particular getting this log x to a positive constant, you need to work slightly harder than the method I've outlined here. In particular, it turns out that this argument, choosing everything independently for each of these large primes, is not the most efficient way of doing things. You can instead do an argument based on the semi-random method in graph theory to do a hypergraph covering lemma, which means that rather than needing to show that the expected number of times everything's sieved out tends to infinity, you can actually do rather better by winning quite a lot as soon as this expected number of times any individual thing is sieved out is more than 1. And so you need some extra ideas to get the strongest quantitative bounds, but hopefully this at least sketches an idea of how to get an arbitrarily large improvement that doesn't use the Erdős-Rankin smooth number trick, and therefore correspondingly generalizes very naturally to polynomials, and therefore allows us to answer the question of Pomerance, even though it doesn't say anything at all for systems where they're coming from sort of higher level sieves, such as the question of Heath-Brown on large gaps between twin primes. This method doesn't say anything about that at all. But maybe I'll stop there. Thanks a lot for listening.
Very good. Any questions?
I try to redeem myself with that. So gaps between sums of two squares can be as big as log x.
Yeah.
Is that expected to be large in some sense? If you read about the Chinese ranking, do your methods go beyond log x?
I don't know. Somehow, at the moment, our methods seem most natural in the case when you've got something that's corresponding to a sieve of dimension 1, and sums of two squares would be corresponding to a sieve of dimension 1/2. So I would have thought that there's different qualitative behavior there, and so maybe our arguments would be missing some fairly obvious tricks and things in that situation, although I haven't thought about it. So my answer is I don't know. But it's good to think about. Julia?
How sensitive is all this to the sets? We
Uh,
can think of lots of sets.
Uh,
Even lots of polynomial sets.
Indeed, there's lots of different sets that one might be interested in with large gaps. Somehow all of this works very naturally when things are corresponding to a sieve problem of dimension 1. So when you transform it through, so all of these arguments need to use some form of this Chinese remainder theorem lemma, otherwise we're just dead in the water and we have no ideas whatsoever, basically. If you're using this Chinese remainder theorem lemma, you've reduced to a situation where you have integers 1 up to y and you want to remove a certain number according to different primes, and the original Erdős-Rankin thing worked particularly well when you were removing precisely one thing for every prime. Our thing works fine provided on average you're removing one thing per prime, and you can prove exactly the same sorts of results that don't just correspond to polynomials if you have this sieve of dimension 1 where on average you're removing one thing per prime. I think that's the most general statement that I'm aware of our results given at the moment.
Anyone else?
Yeah, I have a question. So this idea of you can choose something randomly and then you can choose things really. So that would sort of guess that you could choose kind of everything regally, and that would, but each one would do it as well as if you had chosen the previous ones randomly. Like you could choose things regally and that wouldn't mess you up for later stages. So if that were true, how would the bounds compare to the bounds you get, and also the bounds you get using the Erdős-Rankin method? If you actually better using the Erdős-Rankin method?
So I think you get quantitatively pretty similar results to what we get, and I think you do worse than the Erdős-Rankin thing. Yeah. So so the Erdős-Rankin trick is genuinely using some conspiracy amongst multiple things that you're not taking, it's a gambit, you're not taking necessarily the optimal choice, but in combination this very large number of choices eventually conspire to help you out. our method, I think, is precisely the sort of thing that you described, that it's very similar to the idea of just choosing greedily at each stage and saying, well, there's at least one basically greedy choice that's as good as random. But yeah, I think even if you were very optimistic, you'd still be getting things that quantitatively look essentially the same up to the value of this constant dependent on f. Because when you're looking at smaller primes, sort of concentration of measure style arguments sort of say that a random choice and a greedy choice basically do as well as one another, and it's only really these very large primes where you can hope to get an individual win for that prime. So unless you come up with something very clever and sort of structural, like the Erdős-Rankin trick, that means that you can make many choices that conspire together to help you out, if you're just doing the best choice at each stage, then I think you're basically doing something similar to what we're doing. And our method is really just showing that it is possible to do better with this greedy choice. That, yeah, somehow the greedy choice is probably going to give exactly what we did if you imagine greedy is like random. Great.
I mean, it's maybe super optimistic, but when you talk about this being natural for sets that are the result of a one-dimensional sieve, presumably that's like a one-dimensional sieve with a really good level of distribution or something. So I wonder, like, if you assumed Elliott-Halberstam, for example, could this method approach the P+2 problem or something like that?
No, so somehow, it's slightly different, and as soon as you're using this Chinese remainder theorem lemma, you're finding these very unusual things. So you could try and do our method for the P+2 problem, and you could say something along the lines of this lemma, and this will give you a string of consecutive values of P+2, which is slightly bigger than log x. It will look like what we have there. Unfortunately, that's worse than the original trivial argument that would give you log x squared. And somehow, as soon as you're going through the Chinese remainder theorem lemma, you're really looking for abnormally small prime factors occurring, and it's killed you for anything corresponding to higher dimensional sieve problems, because there's a separate trivial argument that does much better than it.